Do you guys hear me okay?
We can, yeah.
I'm trying a different microphone today that maybe will pick up a little bit better if I'm standing further back. So we'll see. And I have the ATC apparently finding me an even better microphone. Okay, and I'm still sharing the screen, right?
That is correct, yep.
Okay, perfect. That's what I thought was happening. I'm gonna go ahead and turn that off for a minute. Does nobody have their video on except for me? Okay, all right, that's better. Is it? I really enjoy the teaching part of teaching where I get to stand in front of the classroom and see all of your faces when I talk. And so it's okay if some people, want to hide their face, take a nap, or turn the video off, but I need to have some kind of visual feedback when I'm talking. So thank you guys for turning on your video. All right, we're broadcasting live on YouTube. And so what I'm going to do is every week there's going to be a sort of this week in ME1800 kind of a thing that gathers all the information together. Again, all the lectures going to be on Zoom here. I'm not screen sharing anymore. Whose job is it today? All right, Alyssa.
Yes.
It is your job to make sure that I'm presenting the thing that I think I'm talking about at the moment when I think I'm talking about it today. And so if I'm going to talk about the computer screen, I should turn on screen sharing. Amazing. All right. I turned on screen sharing. All right. So again, I'll do one of these things every week for this week in ME1800. It'll be posted in advance-ish a little bit. They'll be out by Sunday for the week to come. Again, we'll always use the same link for the Zoom lectures. When I have the video of the lecture posted, it will make a link to the video here. So yesterday's lecture you can get to by clicking on this one. In just a moment, well, at the end of, as soon as class is over, I'll make the link down here live. But you can actually just find it by going to the page for Professor Bergstrom. You should be able to find it if you search. And I've got all this stuff. The Canvas quiz, I had that ready yesterday, but I forgot to publish it until this morning, but it's on now. Let's just take a quick look at it to make sure there's no questions that are going to be hard to understand. And to do that, I'm going to go to the student view so that you don't just see all the answers when I click on the quiz. All right, so week 1 Sunday quiz due this September 6th. That's this coming Sunday, right? Okay, so I didn't get the wrong due date. Thank you. All right, so let's do the quiz. Before you take this quiz, you should become a basic user at mfelabs.org. I know a bunch of you have already done that or started the process. You should read the 2 pages on safety in the CNC Quick Guide, and you should go through chapters 1 and 2 of Getting Started with CAM. And now take the quiz. All right. Have you completed the steps to become a basic user? There is only one correct answer to this question. If you get this one wrong, don't worry. The quiz is set to give you unlimited attempts. So if you get this one wrong, it will tell you you got question 1 incorrect, and you'll have a chance to go back and fix it. Let's see, question 2. Have you reviewed the safety section in the CNC Quick Guide for Haas Mills? Again, now we actually get to some things where you're going to get to figure out what a service speed is in service feet per minute based on some parameters here. I think there's 15 versions of this question. So if you do choose to take the quiz again, you won't get the same version of the question. It's the same equation, but different numbers. So just so you know that, don't just type in the same number again. And again, another question about service speed, and then just some questions about stuff we're doing. So interning the feed is, we said this yesterday, right? That's done, donuts and coffee for the machinist, that's the feed. And in milling, there's pockets. I think they're in your pants here. It is hot and humid out there. Anybody else notice that? It's hot and humid out there. Let's see, CAM programs, generate tool paths. Yeah, okay. And manufacturing process variables, that's what we're talking about today. And we started yesterday. And art to part is in the title of today's lecture. So we're probably, is it in the title or did I retitle it? It's in the title of the PowerPoint slides we're going to use anyway. Maybe not in the title of the lecture. But we're going to be talking about this stuff today and the important things. We talked about this yesterday. All right, I think we're good to go. There is a quiz with answerable questions. I'm shooting for 10 questions for every quiz. We may end up with a quiz with 9 questions, and we may end up with a quiz with 14 questions. But I'm shooting for 10, and to have them all be equally weighted also. All right, so I am currently logged in as student, so I'm going to not leave student view when I have the quiz open. I'm just going to close. I don't need that anymore. And I can stop the screen share for a second. All right. What kind of manufacturing are we going to be doing in ME1800 when we get to the labs? Does anybody know? You guys do know that we're going to do manufacturing when we get to the labs, though, right? Doug, you were going to say something. You unmuted for a second.
Yeah, is it milling and turning?
We are going to be doing milling and turning. Now, yesterday, I think it was yesterday, I described the difference between milling and turning. Does anybody remember what it is? Just shout it out.
In milling, the cutting tool is moving, and in turning, the workpiece
So in milling, the tool rotates, right? And then it moves sideways and up and down, and it moves through the workpiece material to basically whittle away the material that you don't want anymore attached to the workpiece material. And there's a quote here. There's the art student asked the teacher. The art student asked the teacher. He says, "How do I carve an elephant out of this block of granite?" And the teacher says, "Remove everything that's not an elephant." Right. So that's what we're doing in both turning and milling. What we're doing is we're taking some workpiece material, some piece of stock material, and we're removing everything we don't want. We actually call it drawing a blank on words here, but it's on a slide I'm looking at.
It's a subtractive.
So machining is a material removal process by large chip formation, and both milling and turning are machining operations. So we're going to be doing milling and turning in the lab. Does anybody know why we're going to be doing that in the lab?
It's a pretty useful process for manufacturing.
So they are useful processes. So they're useful processes. Why else are we doing that in the labs? Anybody? I really enjoy an interactive class. People have to talk back when I say anybody. Doesn't always have to be the same person. Michael, you're smiling. What do you think? Why else? Besides, it is useful. I'm going to argue to you that it is the most important manufacturing process in the world. But why else would we do it? Besides the fact that it's the most important manufacturing process in the world. Anybody? All right, I'm gonna start picking
Pretty
names.
simple to
Good,
learn.
Matthew. Oh, Ron, what do you got?
It's pretty simple to learn.
It's simple to learn. I've been doing it for a long time, so I believe that it's simple to learn. One of the reasons that I don't teach the lab part of the class directly is because it was a long time ago that I learned about it. And so you guys know we hire people that recently took the class to be the peer learning assistants. The people that actually teach the labs are people that just recently learned it. We do that on purpose because they remember what was hard to understand. I don't remember what was hard to understand. In fact, I operate the machine pressing buttons, sometimes not even looking at the controller when I'm pressing the buttons, like touch typing. Except you're touch typing with maybe a $200,000 machine that could fly apart at any moment if you press the wrong button. And we'll talk about that too. I have done that. Press the wrong button, or it was the right button, it was the wrong time to press it. All right, so the other reason is that we have a lot of those machines here. We could talk about injection molding, which is also a pretty important manufacturing process to today's society. But all we can do is talk about it because we don't have any injection molding machines on campus. Well, we don't have any injection molding machines in this lab that would be useful for talking about injection molding other than to understand what the concept is, right? We could talk about die casting aluminum, but then we'd have to be really careful. You know what's dangerous about casting aluminum? Does anybody know? Anybody take ES 2001 yet? Casting aluminum is extremely dangerous. Anybody?
Because it has to be super hot.
Say again?
Does it have to be super hot?
It is really hot, and the problem with aluminum is molten aluminum is exactly the same color as solid aluminum. So you looking at it, you can't tell, is it molten or is it solid? Molten steel glows red. So you can tell when steel is melted. When aluminum is melted, you can't tell. So, well, I mean, you can feel the heat coming off of it, but you can't tell. And so that's what makes casting aluminum really dangerous. All right, so we're going to do machining operations in the lab. We're going to do it because we have a lot of CNC machine tools in the lab. We have a lot of CNC machine tools in the lab, partly because the people like me that run the lab believe that CNC machining is, if not the most important manufacturing process in the world. And it's kind of hard because they all depend on each other a little bit, right? If nobody was refining ore into metal, then we wouldn't have anything to CNC machine. But there are no manufactured goods that are usually more than 2 steps away from a CNC machine. I can be convinced that some of them are 3 steps away from a CNC machine. But so my suspenders here, the fabric was cut with a knife. The knife was made on a CNC machine. The little metal buckles were stamped. The stamping dies were made on a CNC machine. So if you look around you, the things you look at are very close to a CNC machine. It is the most common manufacturing process out there still. And so that's the other reason we're going to talk about it. And we like to think we're pretty good at it. So we might as well do things we're good at. You'll notice that I looked at the class lists and it had this information. Let's see, how many people we got? We got 55 people on the call right now. Click yes in the participants thing if you're a first year student and this is your first engineering class. I just want to get a count quickly. Click yes. Some of you are, I know you are. Maybe not, and it's your first engineering class. I suppose you could be taking another engineering class right now. Really, nobody's clicking. You go to the participants tab down at the thing. And oh, there's one. Thank you, Alex. Anybody else? There's more than one freshman in this class. But they're sleeping. They're, they're the people with the video off who have fallen asleep. Okay. How many sophomores we got? Click yes. See, the sophomores are awake. They're clicking away. That's more than half the class. Any seniors that need this class to graduate? Let me clear it. Any seniors that need this class to graduate now? Now go. Couple. All right. So you guys, the seniors that need this class to graduate, you've done a few classes already, huh? You've learned a few things already. So you guys know that no matter what the title of the course is, and no matter what the course description says, especially if it's a tenured faculty member teaching the class, they teach the thing they know about, even if it's not the thing the class is about, right? Anybody seen that? Nod, shake your head. Yeah. Anyway, so luckily for me, I know about this stuff, and this is what the class is supposed to be about. All right, so CNC machining. And does anybody remember the title of this class? It's about 17 words long, clearly written by a committee. Anybody remember? Can somebody read off the title of this class for us?
Manufacturing Science, Prototyping, and Computer-Controlled Machining.
Manufacturing Science. Say it again. Manufacturing Science.
Prototyping and Computer-Controlled Machining.
This should probably be like 4 different classes, shouldn't it? So we've figured out what manufacturing is, though, right? We basically spend this entire week figuring out what the title of the course means. So we know what manufacturing is, right? What's manufacturing?
Making a thing to sell on a mass scale.
Making stuff people want. What's science?
I mean, I've never had to define science before, but I guess I would say it's the study of the world around us.
So it's the study, and we study to better understand it, right? So it's studying something to gain understanding. And often it's studying something to gain understanding when nobody really understands it yet. So it's like new study of stuff. All right. What's a prototype?
Unfinished
it's a
design.
preliminary model.
Could you say it a little bit louder?
It's a preliminary model on which other stuff is based on.
So a preliminary
Okay.
model. Initial or preliminary. Why do we want a prototype?
To make sure the design works.
I couldn't hear you.
Sorry, to make sure the design works.
We will maybe use it to test a design. Any other reasons we might want a prototype? Is it really just to test a design?
Work out.
Say again.
I said to test its usefulness.
To test its usefulness, to see if it works. All right, so it's sort of an initial rendering of something to test it.
To, like show off.
Are there
to
any
the
times?
customers.
Say again.
It's also to like show off to the customers to gain.
Oh, to show off, right? So we might get a prototype to then go find out if the customers want to buy the parts. So if we have a new product idea, we probably don't want to make 6 million of them before we find out if anybody wants to buy the product, right? You don't want to have a container of them coming from China before you've sold one. So we might do this prototype. So we might do a prototype production run where we make a couple hundred pieces instead of a couple million pieces. And so those are some of the reasons we want to make a prototype. Are there any times when you here as WPI students expect to need to make a prototype?
Yes.
An example. Your MQP, class projects. We see people do it for their IQPs occasionally. Christmas time or Hanukkah. We're not picking. But it becomes like Santa's little workshop here just before everybody goes home for break, when they're over there with the laser cutters cutting out Christmas tree ornaments and stuff like that, right? You might just want to because you want to. And that's activity that's okay. So we make prototypes, so we make stuff people want. We're going to study it. We're going to specifically study this prototype manufacturing, and CNC machining and milling and turning are excellent ways to make functional prototypes. So that's another reason that we focus on that in the labs. All right, so prototypes in a prototype doesn't have to be a one thing, and prototypes do not have to be manufactured the way the final part will be manufactured if it's a mass production thing. So has anybody ever seen a K-cup? Like a Rake machine K-cup? So I had a task a few years ago, and it was to make something that basically looked like a K-cup, except they wanted it to be made out of aluminum and not plastic. But it had to have the thin walls like the K-cup had and the thin bottom. And so in a manufacturing setting, you would stamp those. You'd make them the exact same way you make Coke or beer cans, right? So when they go to volume production, they're going to make it in a stamping machine. They're going to make, I don't know, tens of thousands, hundreds of thousands a day in that kind of a process. But we only needed 50. And we billet machined them on a lathe. That's much more expensive, but it's a lot cheaper than designing the factory to make them the cheap way. So you don't have to use the same kind of manufacturing processes when you're doing prototyping. We're going to use CNC machining. By the way, billet machining, that's technobabble, right? If I say I billet machined something, what does that mean? What is the billet?
The billet is the raw workpiece.
The billet is the raw workpiece material. And so a billet is a solid chunk of metal, or I suppose you can have a billet of wax, or you can have a billet of wood, although usually we call it a board when it's a billet of wood. So yeah, billet machined, and when I said machined, you got that already. All right, I'm going to talk about slides here for a second. So let me turn on the screen sharing. All right, and did I turn on? No, I didn't quite turn on.
No, not yet.
Now I have turned on the screen sharing. All right, so I said that machining, and so both turning and milling are machining operations. I said that machining is a material removal process, and we got that. It's like carving the elephant out of the piece of granite. We just remove everything that isn't the elephant. Now, it's a material removal process by large chip formation. Anybody think of an example of a material removal process by small chip formation?
Like sanding?
Sanding, grinding, those abrasive processes. Those are same physical mechanism, but it happens on a smaller scale. All right, so what the image here shows is there's a cutting edge. It's moving through some workplace material, and we're going to see this image throughout the class. There's a chip that's being formed. That chip has a thickness. There's an uncut chip thickness. That's the amount of material that we're about to remove. One thing you might notice, and it's not that clear in this diagram, but the chip thickness and the uncut chip thickness are not the same dimension. They're not the same number. And the chip is often thicker than the uncut chip thickness. Any guesses why that is? Because you would think you skive off some material, the amount you take off is just going to curl up and go up the tool. Any guesses as to why? We put a lot of energy into this process where we're making the chip. And as we put all that kind of energy into it, it deforms the material a little bit, right? So if you push on anything, you deform it. And so you actually get plastic deformation in here, and you squish the material around a little bit in addition to cutting it off. All right, material removal process, large chip formation. Let's go to, oh look, there's a video behind that one. All right, so here we see the so the workpiece material in this video is a plastic. I think it's a Delrin. Right here, let me ooh, big screen here. You guys can see the mouse moving around. Nod your heads. Yep. Okay. Good. So this surface that we see on the top of the tool is called the rake face of the tool, and we're going to get into that a lot later. The rotation here, if I play a little bit, you can see the direction of rotation. All right, and so the feed now is going to be perpendicular to the axis of the material. So it's going to feed in and form a chip on the top of the part. And so all machining happens exactly this way, sort of. But the physics of the process at the tool chip interface is exactly the same, no matter what kind of machining you're doing. And I think we switch the view here in just a second. All right, now we're looking straight down the rake face of the tool, looking at the cutting edge, and we're feeding along in this direction. And we see that chip forms. And as the chip forms, back a little bit. So the chip's forming there. And we can get over here so you can see. So here's our uncut chip thickness. Here's our chip thickness. The cutting edge is right here, and we're looking straight down the cutting edge. And the chip slides again, it slides along that rake face of the tool. And let this play out. All right, so this is an example of an outside diameter turning operation. So remember we said in milling, the tool spins. In turning, the workpiece spins. And the tool moves laterally in and out and along the process. So we've got some process variables that we're talking about here. So this uncut chip thickness, that's a process variable. We get to pick that. We choose it when we choose the feed rate and the angles of the tools. The cut chip thickness, that is a dependent variable. We don't get to pick that. That depends on the physics of what's happening in the cutting operation. So depth of cut. We've got a final diameter. We've got an original diameter. The depth of cut is the difference on one side between the final and the original. So the difference between the final diameter and the original diameter is 2 times the depth of cut, right? And so what you can see immediately is these turning operations, they're very good at making axisymmetric parts. So a turning operation is going to be very good at making an axisymmetric part so who's had the CAD class? Raise your hand or something. Right, so in the CAD class, one of the ways that you make a solid is by a revolve, right? And so this is sort of the opposite of the revolve that you see in the CAD class, except we actually remove material instead of just virtually do it with pixels. All right, so next slide. Back to this. When I'm screen sharing like this, I'm gonna have to use the other monitor because the control keeps popping down when I'm trying to change tabs. All right. All right, so relative motion between, oh yeah. So this relative motion, this velocity here is also something that we got to understand. Now, based on what we've already talked about, what do you think the velocity is? We've already talked about this. We examined it on the board yesterday, but this velocity, the speed of the cutting edge moving through the workpiece material, where does that come from? Does that come from the feed?
Primarily, it comes from, if this is a mill, it would be tool rotation. It's the surface
So
feed.
the feed can contribute, but it's almost always negligible. It's that surface speed that we talked about yesterday. So this velocity is almost entirely comes from the surface speed. So the speed of the rotation, remember we did the circle and we did the circumference, and it's how fast does it go around, and we figured out the units, right? All right. So all right, so here's, have we seen some milling operations? Here's some milling operations. So that's billet. That's a billet of material. And the goal in these milling operations is to, yeah, he's got all kinds of stuff in there. And that's the video you just saw. So turning workpiece rotates, milling the cutting tool rotates, and the spindle. The primary process variables in manufacturing, in machining, are the feed, the speed, and the depth of cut. What is the feed again? guys
Professor,
remember
do you
what the
want us
feed
to be
is?
able to see the board?
Oh, thank you. Can you guys see the green okay? I think the blue shows up better, but I used green there. So what's the feed again?
How fast the tool moves.
It's how fast the tool moves laterally through the workpiece material, or up and down through the workpiece material, right? So it's the sideways motion, you can think of it as. And you should think of it as sideways motion only if you can remember that up and down is also a side. It's like the top and the bottom side. So this is the feed. What are the units for feed, do you think? Or what should the units for feed be? Because I said engineering's math, just a bunch of word problems, cancel the units, right? Can't cancel the units if you don't know what they are. So what should the units for feed be?
Rotations per minute.
Inches a minute.
Inches per minute? Could you conceive of any other units you might use for feed?
Feet per minute.
You could use feet per minute, but this is sort of length over time, if you want to make it generic. So if we're using
Meters per
metric,
second.
if we're using metric, we usually do millimeters per minute. What other units might be interesting if you're visualizing the turning operation or the machining operation, whether it's turning or milling?
Miles per hour.
Yeah, miles per hour. That again is just length over time. So this is length over time. And we can change the units around in length over time, but it doesn't really impact the math of the unit conversions. But what if we talked about the inches, so the length that it goes for every revolution? So we talk about how far does the tool move sideways each time the tool turns around. And so we will often do inches per revolution in a turning operation. And then in a milling operation, so when we looked at our milling cutters, we look at the bottom of a milling cutter. This is why I'm an engineer and not an artist. So we have these cutting edges, and so there's 1, 2, 3 cutting edges. Oh, it looks better. There's 3 cutting edges on the bottom of my milling tool. And so instead of inches per revolution, we might do inches per tooth. The problem with that is not everybody calls it a tooth. Some people would call it an inches per flute. because each cutting edge on a milling tool is called the flute. And again, that's more technobabble as you're going to have to pick up as we go along. So we'll look at inches per tooth. Inches per flute is exactly the same thing as inches per tooth. What's the conversion between inches per revolution and inches per tooth?
Depends on how many flutes.
Right? You got to multiply by, what is it, tooth per, we want tooth on the bottom, so 2. Right? It's how many teeth per revolution. So how many teeth, and same thing when we did our surface speed, it's how much distance per revolution. So how many circumference per revolution, as we say. All right, so if we're talking about feed, you kind of have to specify the units. You can't assume that they know the units if you just say feed. So you have to say feed in inches per revolution, or feed in inches per tooth, or feed in inches per minute. If we're looking at the program Go, it's easier for us to intuitively visualize usually this inches per minute. If we're programming, usually the more interesting thing for the physics of it is this inches per revolution or inches per tooth. So those are the things that we're going to see in when we look at feed. All right, so I got feed, I get speed. So what did we say the speed was again yesterday? We introduced this yesterday.
How fast the tool is rotating.
It's how fast the tool is rotating or how fast the workpiece is rotating if it's a turning operation, right? So speed. What are the units for speed?
RP rotations per minute.
So we can get rotations per minute. We like to call that RPM, but when we're trying to cancel our units, we sometimes forget that RPM isn't a thing. And what it is really is rev per minute. And if we write it as rev per minute, it's easier to remember how to cancel the units later. I don't care how you write it when you're doing your work for yourself, but that's what I do. Anybody ever take a test to get points taken off that were unfairly taken off? You get points taken off that it was a mistake in the grading. We've seen this happen before. I mentioned that I went to WPI here, and A term, freshman year, physics. Anybody taking physics right now? I don't know. I can't see everybody. A term, freshman year, physics. Physics was the class that I did well in freshman year. In fact, physics was the only class that I did well in freshman year. But on the final exam, I had a 99. And the TA that graded the exam took off 1 point during the steps of one of my problems because he didn't understand engineering notation, because he was a science TA. And in physics, you write, 6 times 10 to the 6th, right? In the middle of solving the problem, I was using engineering notation because it takes fewer pen strokes. I did 6E6 in the middle of my calculation. And then at the end, I said the answer was, 6 times 10 to the 6th, because I knew the physics guys wanted to have the answer that way. And he took off -1 because he thought I meant e to the 6th. But if I had meant e to the 6th, I couldn't have got the right answer for the problem. And I went and argued with the professor. And the professor agreed with me. I did not deserve to have that point taken off. And then refused to give me the point back. Because it wasn't going to change my grade. So keep that in mind when you're arguing about your points later. If it's not going to change your grade, maybe you don't have to argue as much. But But I will say that, especially with these automatically graded quizzes in Canvas, it is entirely possible that my quiz is broken, not your answer. So if you keep getting the same thing wrong and you know you did it right, just tell me. I can't fix it until after everybody's finished the quiz, but I can fix your grade. So keep that in mind. It is entirely possible that I'm wrong, not you. PVs manufacturing, speed, revolutions per minute. Okay. What other units do we have for speed? In our cutting equation, it was important, right? I can draw that again. So I got my tool. I always draw the tool in green. I always draw the workpiece in blue. Workpiece here. And oh, I don't have a red marker, but I'll use orange. My chip. All right, so the speed we're talking about.
Professor, I can't really see the blue.
You
I
can't.
don't know if it's just me, but I can't really see the
You can't see the
in
board.
the diagram. I can't see the blue in the diagram.
Oh, yeah, the blue marker seems to be dying. Let me make the blue into brown. The brown doesn't work that much better. I gotta get some new markers. I can
Thank
get
you.
back to the screen share. All right, so the is it any better? Not really.
I can see it a little better, but yeah.
It's the same diagram that was on the slide. We'll be drawing this diagram pretty much every lecture for the next 2 weeks. So you'll see it again. And I'll get some better markers. But it's this velocity of the cutting tool moving through the workpiece that we really care about, which is not revolutions per minute, right? So we call that the surface speed. And how do we convert from surface speed or from RPM to surface speed? Anybody remember?
Multiply by the circumference.
So we need the diameter. We need pi. And pi times the diameter equals the circumference, right? And that is units of inches per revolution. And so if we have inches per revolution times revolutions per minute, that will give us inches per minute. But remember, I said when you can't see the orange, can you at all?
I can see it fine.
Okay. It's hard for me to see the orange. I'm glad you guys can see it. Inches per minute is not how we talk about surface speed in machining, though. We need to make this go to feet per minute. How do we go from inches per minute to feet per minute?
Divided by 12.
So I got 12. I need feet per inch. So I need the 12 to be on the bottom. So I got to divide by 12 inches. Good. And that flips over. Right? And so that will give me feet per minute. Except just like we like to write RPM, nobody ever writes feet per minute when they talk about surface speed. They write SFM, surface feet per minute. So you'll see SFM and RPM all the time, and you just need to remember that RPM is revs per minute and SFM is feet per minute, and then you will be able to cancel the units. And has anybody ever used Google to answer a homework or quiz question? Yes, Nick admits that he has used Google to answer a quiz or homework question before. George also. I imagine there's people that if I scroll the screen, that more people admit it. And those of you who didn't admit it probably lie about other things too. So I encourage you to use Google if you don't know the answer and you don't know where from your lecture notes or from materials that I published to go look it up. Now, often the answer will be included in the stuff that I've published and told you to look at. Sometimes it's faster to find it by using Google though, and that does not offend me. So feel free to use Google. Google doesn't always have the right answer, or it might have a better answer than the one I think is the right answer, but I'm the one that does the grading, so excuse me. When you Google, go from RPM to SFM. Turn on the screen sharing here. This is dynamic lecture content. Oops. I wish there was just a button I could press and it would just flip from one to the other. And then I wish the zoom controls didn't move when the screen sharing was on. When you Google it, you'll see an equation that looks like this. SFM times 4 divided by tool diameter. That's not what we just wrote the equation was though, is it? What's 4? Where'd that factor of 4 come from in this equation that you will find if you look it up? What's 12 divided by pi? Roughly 4. And often when we're doing this conversion, we don't need the exact number. We need to know sort of what's the right number. And so you will often see people use these two equations here, or this equation, or its inverse, in converting from SFM to RPM. That's probably good enough. If I don't want to do the math out, I open up the CAM software because it has 2 input boxes, one where you can input the RPM and one where you can input the SFM. And if you type in one of them, it calculates the other one automatically, as long as it knows the diameter of the tool. So I often cheat by typing in the CAM software. It doesn't matter to me how you get the correct answer, as long as you have a method that works, that is repeatable, and you can do it again. So, all right, what else? We watched some of this yesterday. Maybe if there's time at the end, we'll come back and look at some bloopers. And so you guys, has anybody opened up Esprit and taken a look yet? A couple of you have opened it up and taken a look. And we're gonna be using it a lot throughout the class, so you'll have plenty of time to look at it. But here's some examples of some of the things that impact the way the part gets made. Now remember I said 47. Okay. Now remember I said that feed speed, depth of cut. We didn't do depth of cut yet. Let's jump back to depth of cut. What's depth of cut in milling? Or what's the depth of cut and turning? We did depth of cut and turning, right? I showed you the original diameter, the final diameter. Half the difference between the original diameter and the final diameter is that depth of cut. It's how far the tool comes down. We do our pass sideways. So that depth of cut and turning is very intuitive. What's the depth of cut and milling?
Depends on the amount of material you want to take out. Each pass you go with the CNC.
Yeah, so there's actually 2 dimensions in milling that we got to consider depth of cut, right? We've got how far down does the tool go into the material each time it goes through the material. And we've got how far over does it come into the material. So what percentage of the diameter of the tool is engaged with the material, as well as what's the depth into the material. So feed speed and depth of cut are the 4 most important parameters in machining operations, because depth of cut has 2 parts. But let's look at it. So anybody know what a pocketing operation is in milling? Go ahead, George.
It's the removal of a material inside of a part.
Right. And so this picture, I'm still showing the slide, right? All right, so the picture here shows a couple of pockets that get removed from the part. So there's the circular one here. There's actually another pocket at the bottom of that you can't really see here. There's this circular pocket, And so for the tool to remove the material from the circular pocket without coming in from the side and damaging the side of the part, it's got to come down into the workpiece material, and then it moves out. And this tool path looks like it's coming in a spiral out. So it's coming in at the center, and then it spirals out to the outside, stepping over a little bit more each pass to make that part. So to make this pocket, let's look at the dialog box here that we fill in numbers here. We've got cut speed, RPM, SFM. We know what that is, right? And if you put it in on RPM on one side, it'll calculate the SFM for you. We've got our feed rate. There's per minute or per tooth. And so we understand what that is. And so this one, when it's doing that spiral out, the tool is spinning at 12,000 RPM. And it's moving out at 288 inches a minute. That's pretty fast. All right, so, and then we have a Z feed rate. That's how fast does it move if it's moving down in the material. So this pocket right here is happening 12,000 RPM, 288 inches a minute. Now it's doing what we call a climb cut. And we'll talk more about that later, but we have to specify, do we want it to be a climb cut or do we want it to be a conventional cut? And climb just means that the rotation of the tool, the action of the cutting tends to pull the tool into the workpiece. In a conventional cut, it's rotating, it's going around the other way, so the rotation is tending to push the tool away from the workpiece. All right, so stock allowance on the walls, we get to tell it, do we want to go all the way up to the feature, or do we want to leave a little bit of material and come back later? We got to tell it how we want it to enter. We never want the tool to plunge straight down into the material. We want it to always be moving sideways because these end mills are not designed to plunge straight down. They're designed to cut sideways. So we do a helix on the way in. You got to give it all these parameters. Then that's just this one tab. There's 1, 2, 3, 4, 5 tabs. All of these things, those are process variables. These are all things that you get to change. The ones that impact the physics of the machining are feed speed and depth of cut. But all of them are important. So if you said plunge into the part instead of helix contained here, what the machine tool would do exactly what you told it to. It would come over, it would come straight down in the center, and the tool would break. So I guess that does impact the physics of the operation, in the fact that you won't be doing the operation if you set that parameter wrong. Let's see what's on the next slide. Oh yeah, feed speed, depth of cut. Guessing, not recommended. Carbide, explosion. Next week we'll have an assignment where you all get to publish a haiku. But haikus are a hobby of mine. Feed speed, depth of cut, guessing not recommended. Carbide explosion, how do we avoid guessing? Yeah, there's a bunch of haikus in here. Oh, I thought the next slide was going to tell us how we avoid guessing. You guys have to tell me how we avoid guessing. Has anybody started the chapter 2 in the CAM book yet? I guarantee you that chapter 2 is all about not guessing, figuring out feed speed and depth of cut. But how do you imagine you avoid guessing what the right feed speed and depth of cut are?
There are parameters you can follow with the size of the bit you are using and what material you are cutting to specify how much material.
How do you find those parameters, somebody? How do you know what they are? I know what a lot of them are off the top of my head because I used that tool before, but you haven't, so you don't know.
I've used them in high school, so I've.
So how does somebody find out what these parameters are? Look them up in a reference book. The tool manufacturer, for example, will publish what the appropriate feed speed and depth of cut are for this tool in this material. There are guidebooks, and we're gonna show you how to use the guides for the tools that we use in the lab here. It's easy for you because we've got that stuff in charts at that mfelabs.org website. So if it's a tool that you got from us, you can just go to our website. We've corralled that information for you so you don't have to go hunt for it. So we avoid guessing by looking it up. When we grade the CAM assignments, the only thing that people usually lose points for, if they've actually followed the instructions, is not putting the correct feed speed and depth of cut, because they guessed instead of looked it up. So don't guess. And what else we got? It's time to stop. I've gone over 4 minutes. It's gonna pretty soon we're gonna have to assign somebody to make sure I don't go over the time too. Because if you haven't figured it out, I enjoy talking. And I could talk for hours and hours and hours, especially about a topic that I care about. Next week we will do Tuesday, Wednesday, and Thursday. I might put a poll. I'll put a little survey on the Canvas site to see if people prefer to do 8 o'clock or 11 o'clock for that Wednesday. I prefer to do 11 o'clock because it gives me more time to think about it and get ready without rushing in the morning. But if people can't make it at 11 and they want to do it at 8, if there's enough people that vote that way, we'll switch it back to 8. Because I imagine, even though they didn't schedule it, they didn't schedule something else for you to do at 8 on Wednesday morning either. For most people, I'm sure there's probably some labs that conflict. Thank you very much. Feed, speed, depth of cut. Don't forget it. If you remember anything from today, remember how to do these unit conversions. You will need to do them in order to satisfactorily complete the quiz. Although you could type Google. I guarantee you that there is no question on that quiz that you can't figure out the answer from Google. And there will be no question on any quiz that I give that Google doesn't contain the answer. You may not, it'll at least contain the equation. You may have to type in the numbers. Thanks very much. Get an A on the quiz. You can take it as many times as it takes to get an A. If you don't finish the quiz with 100%, that's on you, not me. Even if I didn't teach you the stuff in advance because I just told you to Google it. Thanks a lot.
The first lab is Monday, right?
Yeah, if you have labs scheduled on Monday, and we'll send out the schedule to everybody to remind them when they need to go.
Thank you.